Okay, welcome back. Episode one, Season one, episode five. Excited to be back here after that great episode last week with Morgan. We talked about genetic engineering. And I have a bunch of ideas for different episodes, but I think the pieces are in place. Okay, for us to start putting some real concepts and ideas together to understand bigger questions, existential questions. So today what I wanted to talk about, I think we have enough foundational knowledge to really gain a grasp on this topic. And I was having dinner with my family over the weekend and this question came up. They're all non-scientists and know that I study, I'm in science and stuff. And so they asked me, and I've been asked this before, but they asked me, Tom, why haven't they found the cure for cancer? And they sort of couched it like the mRNA for COVID was so easy to make. We made it in a year. How come we can't just find the cure for cancer? It doesn't make any sense. Well, it was too long of a conversation for me to answer that at a dinner party, So I figured I'd answer it here. My family doesn't watch the podcast that I know of, but maybe some of you have the same question. So yeah, let's talk about that. I think we actually have the foundational knowledge to understand why it's so difficult, why it's such a hard disease to treat and cure. So we're going to put together a lot of different pieces from different, previous episodes. Now that we have some that we'll draw from some of that previous discussion. And again, I'm going to be healing Mythic plus Dungeon as a Discipline Priest. Blah, blah, blah. There's a YouTube component as well. So if you want to watch the VOD, you can watch the VOD. Yeah, it's kind of annoying affixes this week, so I hope it doesn't take too much of my attention, but it should be okay here. Okay, so let's get started here. So why is cancer so hard to treat? And why is it so hard to find a cure? Well, in order to sort of answer that question, we have to establish some baseline knowledge about cancer, how it arises, and that'll help us better understand. If we know where it's coming from fundamentally, we can better understand how challenging it is to treat. So, without further ado, I guess. It kind of takes me back to episode, I think it was episode 3 in the series. If you want to go back and review that, or we can just, I'm going to give a quick brief review here, where we talked about, I sort of defined cancer, what it was, where it came from. Let's just review. So cancer is a problem with your cells in your body, right? So a cell in your body has genetic material, has all of your DNA, and every cell in your body has the same DNA. So every cell in your body has your DNA to make you you. It's just that every cell, it doesn't need to use all the same DNA, right? Like a tongue cell doesn't need the same genes as an eyeball cell, or a brain cell doesn't need the same function as like a cell in your colon or something. So there's different functions, so there's different need in terms of genes that need to be used by each cell type, and the other genes are then just turned off. Meaning they're just sort of like they're still there, but it's like the cell maybe I forgot they were there, but just doesn't use them, doesn't need them, doesn't use them. So they're like turned off. But every time a cell divides, it has to replicate all of the DNA. Even the stuff it doesn't use gets replicated, so that the daughter cells, or the two cells that it splits into, have the same DNA as the starting cell. That's just how cells divide and work. They pass along genetic information from cell line to cell line. Okay, so if every time a cell divides, it needs to replicate its DNA, we need to make that pretty perfect, that machinery, so that we get, you know, it's 6 billion base pairs. So we need some machinery, some replication machinery that is pretty accurate, right? But it's impossible to get machinery that's 100% accurate. There's always going to be mistakes. There's always going to be errors when trying to copy the entire genome. It's unavoidable. But evolution has provided, you know, given us a long time to sort of, our body knows how to work around these imperfections, and 99.99999% of the time, it's not a problem. These mutations happen. Our body knows how to deal with them. We either fix them or the cell is out of commission. It can't function without those, with that mistake. It just can't. It can't live. So 99.999. So today, sitting here right now, like throughout the past 24 hours, you've probably had hundreds, if not thousands, of mutations in your body, and your machinery's just fixed it. You haven't even had to do anything. It just happens automatically. So you have these mutations that happen all the time, and we just never know because our body takes care of it. Now, very, very rarely, when a mutation occurs and our body doesn't fix it and take care of it, it'll actually go through and the cell can live. But those mutations, even after it makes it through, those typically, most of the time, do absolutely nothing. It's like you don't even notice. The body doesn't notice. Nothing happens. Nothing changes. Status quo remains the same. But then, very rarely, a mutation will happen that actually causes problems. And it's super rare. You think of how many mutations happen in your body every day, and none of us get cancer every day, so it's just super, super rare. And what has to happen is a mutation occurs in the part of the cell sort of machinery that is in charge of the internal clock, where how fast, like cells have sort of this like internal clock where they know how fast they need to divide. And they'll just divide on that schedule, right? Well, if a mutation happens in that machinery and the cell thinks it needs to constantly divide, I need to constantly divide, I need to divide again, I need to divide again and again and again. All of the baby cells or daughter cells that it splits into have that same mistake. And so all of those cells are thinking, hey, I need to divide again and again and again. Well, over time, mutations build up. You get more and more and more mutations. And that's when it starts to become a problem. Where eventually there's going to be a mutation that is going to help the cells that are mutated avoid the immune system. So that brings up the second part of cancer, where even if the cells get mutated to a point where they're constantly replicating, our immune system recognizes that as a problem, and our own immune cells kill the cancer cells, kill the mutated cells. That's part of our defense mechanism. It's been around, we were humans, you know, it's been around forever. So our own immune system kills the fast-growing cells that shouldn't be growing that fast. It will just kill them. So eventually what will happen, though, if the cells, you kind of reach this like homeostasis where the cells are dividing faster than the immune system can keep up. So yeah, the immune system's attacking and killing as many as they can as fast as they can. But eventually, like, it gets to a point where the cells are just dividing too much, too fast, and mutations start to build up, and then eventually a mutation is going to happen in the machinery that helps them avoid our immune system. So now that is the definition of cancer right there. So As soon as our bodies cannot recognize the cancer cell anymore, as long as our immune system cannot recognize the cancer cell anymore, that's the definition of cancer. So now the cancer cell can just grow continuously without problem. The immune system has no idea it's there, it's kind of blind to it. And now all of the daughter cells want to replicate really fast. And so now you start to get a bunch of these rapidly dividing cells that all they want to do is continue to divide. And as they continue to divide, they just keep getting more and more and more mutations. And it becomes cancer and a problem. So the point of all of this, the whole reason we had this discussion, is to understand and realize that every cell is different. Every cell is expressing different parts of the DNA code. So different mutations are going to happen in different cell types that are going to affect those cells. So what that means is, like, a brain tumor is much different than a lung tumor, is much different than a skin tumor. So every tissue has different mutations that make that cancer unique. And what's another even further difficulty, since the immune system, or since every person has a different mutation, so like every person's cells mutations are completely random and completely different from any other person. There's similarities in certain cancers, but for the most part they're just kind of unique to that patient. So every patient then becomes unique. Their cancer is different than the person next to them. One person's skin cancer is different than another person's skin cancer. And that is the problem, right? So it's not like treating a disease that we know how to treat, where it's just one skin type or one tissue type. It's different tissues, different mutations in every tissue, and then every patient is unique. So it's not like finding one cure, it's finding infinite cures, right? And what's crazy, I talked about this in the episode 3, is even tumors of the same cancer type in the same patient. Like, let's say 2 different melanoma skin tumors metastasized and went somewhere else. The 2 tumors in the same patient will respond differently to therapy because they have different mutations. That's how difficult it is. It's like it's not like treating Alzheimer's or something where we can understand the cell type, we can understand the underlying how disease progresses, so we can try to develop medicines that fight that. Because we can't do that because every cancer is different, because all the mutations are different, and then even two of the same cancers, multiple myeloma in 2 different patients, is going to have different mutations, and therefore respond to drugs differently. Isn't that crazy? It's sort of mind-blowing. And so when you think about it like that, where no single drug is going to ever cure all of the cancers, ever, it kind of gets me excited about this idea of the fundamentals. Like, fundamentally, we have to go in and fix the problem where it has occurred. And so, maybe you can fill in the blank here. How do we do that? Well, we talked about it last week. Genetic engineering. That has got to be we are going to die here. That's got to be the long-term answer. Because if we can develop a system, a platform technology where we can find a cure for... Oh no. Sorry, we're getting absolutely... I'm trying to save a wipe from happening here. Okay. I honestly think we're gonna be okay. Okay. So if we can develop a system that we can make, it's called patient-specific or precision-based medicine, where we can create a therapy specific to a patient based on their cancer model. Whatever their cancer is doing, we can make a therapy specific to that patient, patient by patient. And that's really hard to do, but that's what it's going to take. And so it's a lot different. You can't think of curing cancer like you would think of curing any other disease, because it's not the same thing. It's like curing cancer with small molecule drugs. Like, you'd have to cure an infinite amount of diseases, because every tumor is different. So we develop a platform technology like genetic engineering, CRISPR, where we can create a guide RNA specific to the patient's mutation that we want to fix. All we have to do is change the guide RNA, and that's super easy to do. Use the same delivery vehicle, same everything, just change a couple base pairs in the guide RNA, and theoretically we can cure any cancer, any tumor, by fixing the mutation. Now, we are far from that, but that's what gets me excited about genetic engineering. That's why I had Morgan on last week, because it allows us to have this conversation. What it's going to take to cure cancer. So what we're doing right now, I guess pre-genetic engineering, pre-CRISPR, we've solely been working mostly with chemotherapies and monoclonal antibody therapies. I guess there's three major pillars, I would say. So there's chemotherapy, there's monoclonal antibody therapy, so immunotherapy, where we're using mutations in the cancer that are making certain markers on the cell surface overexpressed, and we can use that for targeting, so that we can target the cancer. And then the third thing is immune checkpoint inhibitors. All that means, that's sort of a mouthful. All that means is we're trying to help the patient's immune system recognize the cancer again. Like, we're trying to knock out whatever the cancer is doing to avoid the immune system, and just try to get the patient's immune system on board. Like, oh, here's the cancer. This is what I need to be attacking. So those are the three pillars: chemotherapy, immunotherapy, and immune checkpoint inhibitors. Yeah, so... Or a combination of all of those as well. But again, we're sort of just treating... It's not specific necessarily to the cancer. Sort of. Immunotherapy is, but it's not like we're using a therapy specific to the mutations that are happening in that person's DNA. These are still sort of broad stroke therapies where we're kind of passively targeting the cancer, somewhat actively targeting the cancer with antibodies. Yeah, and a lot of these things have their own set of problems and toxicities and things. So we're definitely far from the cure as is. We have things that work, right? And we have like a decent understanding of what we're doing. There's definitely no definitive cure for any cancer that I'm aware of. Like, a patient comes in with this cancer, you do this to cure them. That's not a thing. Every patient's different, and the doctor has to make decisions and choices based on the knowledge that we have currently. And that's why it's called practicing medicine, honestly, is because they're getting practice, like, and they're helping future people with cancer by, you know, testing different drugs, different doses, you know, and just trying different things, trying different therapies, different regimens, different orders of drugs. Yeah, and it's hard. It's really, really hard. And I've seen this all firsthand. I worked at Children's Cancer Hospital during my undergraduate degree. This was like 10 years ago, but yeah, I saw this all firsthand. A lot, you know, cancer is very near and dear to me. It's something that I have a lot of motivation to study, and, you know, just try my best to push the field further so that people don't have to go through some of the stuff I saw them going through. And I'm sure a lot of the listeners, a lot of you guys have seen family members and things going through just what chemo does to the body. You know, that I saw so many situations. This was 10 years ago, so we've progressed so much further even in just that amount of time. But there were situations where, like, I knew, like, I had full faith in the physicians and doctors that I worked with that we were doing the best we could, but I also knew that our best simply isn't good enough. Like, this isn't gonna cut it. We need more. We need better therapies. This ain't it. This ain't it. That's what's motivated me to try to, I don't know, just push the field forward any small amount that I can, that I'm capable of doing. But yeah, so that is why cancer is so hard to cure. And it's not like, you know, I hear this all the time from members of my family mostly, that Big Pharma is hiding the cure from the world because they're in it for the money. If they cure cancer, how are they going to make a bunch of money? Because then no one will have cancer anymore, and cancer is like the biggest disease, and there's a lot of money in treating cancer. I don't mean to laugh, but it's super funny when I hear stuff like that, because straight up, it is literally the opposite of that. Like, companies have so much motivation to find a cure, specifically for money, but even more than that is just for, like, the recognition, like, that's Nobel Prize. You go down in history for something like that. Like, people will never forget your name for stuff like that. There are so many people around the world, including me, people just like me, people smarter than me, physicians, clinicians, who are studying cancer and trying to find a cure for different cancers. It's really hard to find a cure, as we just talked about, but, you know, they work on a specific cancer model and just try to find a cure for that cancer. There are tens of thousands of scientists, hundreds of thousands of scientists probably working on this. There's no hidden agenda here. Like, it would take some, I don't even know what it would take. It's just literally impossible. Literally impossible to hide something like that. It would get out in the scientific community so fast. I think it already is out. I mean, it's CRISPR. It's genetic engineering. That's what's going to do it. We just have to get there. It's probably, I don't know. And then there's going to be politics in it as well, because we're, like, altering people's genes and DNA and stuff. But realistically, I don't know. Clinical trials on gene edit, like CRISPRs, are already ongoing, currently ongoing. So, I don't know, 10 years. I'd be really, really, really excited to see where we're at in 10 years. So that's yeah, that's why cancer is so hard to cure. So next time somebody tries to bring that up or something, maybe you can talk a little bit about it, some educated form. And we did the key just in time. So yeah, that is this episode. I thought it was gonna be a really cool episode because we have like all the pieces to understand that concept, right? Where we understand delivery vehicles, we understand what it takes to deliver mRNA now. It's a fragile cargo, it's a fragile therapeutic that we need to package into a delivery vehicle. And then it won't get degraded. And then gene editing, so we can use RNA to vaccinate, but we can also use RNA as a guide for gene editing. So we can cut out mutated genes, just cut them out, replace the bad genes with fixed good ones. That's the idea. And as Morgan talked about, we only need like 5% efficiency because those cells will then grow normally. And maybe it'll take, I don't know, it'd be interesting to see the future. Maybe you do like a combination of gene editing therapy with even like immunotherapy or something. I don't know. There's probably some combinations and stuff. 10 years from now, the field is going to be so different, I think, of how to treat cancer. So it's really exciting. I feel like we're in the future, kind of. You know, like the future that was written in like the 80s where flying cars and like all these little robots in the body and like all this crazy stuff. I feel like we're kind of like getting there. We're super close. I just feel like the science is just expanding so fast with all this collaborative effort that the internet provides, and yeah. So I'm excited. Cancer, it's a hell of a disease. It's honestly, it's infinity disease. It's not just a disease. It's infinite diseases. Not really infinite. It's how many people are on the planet. That's how many diseases it is. Because if you get cancer, if you're unfortunate enough, or if I'm unfortunate enough to get cancer, my cancer is going to be unique to me, and to me alone. It's going to respond to drugs, therapies, anything, radiation, anything differently than the person next to me. It's a crapshoot, because all we have right now are sort of like blanket, broad stroke therapies. But we are moving into this more precision-based or patient-specific therapies, and that's where we're headed, certainly in the future. And so hopefully you learned something there. That was fun for me to talk about because this is my life every day. So yeah, I love talking about this. I love talking about cancer. Sounds kind of weird saying it like that, but yeah, just spreading the knowledge, I guess. So yeah, thank you for listening. Next week, I think I'll do an episode on specifically what I do for research. I'll talk about what I do because I got a couple people asking me about that. I'll put an episode together for that. And then I want to do another interview. So I have a couple ideas. I don't want to spoil it. I have a couple ideas. And they should be pretty good. One of them is going to be really good for sure. The other one I got to work out some kinks. But we'll see. Thanks for tuning in again. If you want to watch the VOD, there's a video on demand on YouTube of the dungeon and some discipline-free stuff. Or podcast is just on like Spotify and stuff. But yeah, thanks for tuning in. Let me know if you have any questions or comments or suggestions. And thank you.